Hello, I am Tara Haydari, and this is Lab 3. We're going to talk about black holes. So, the goal of this lab is to estimate the mass of the black hole using the analysis from the star's motion. And our system is a star. Now, we're going to assume the net force on the star only includes an input from the black hole located at the origin, specifically the gravitational force of the black hole on the visible star. Now, the time between the data points in the trajectory is 1 day, and if we want to convert that to our SI units, it's 86,400 seconds. The little bit of motivation behind this lab is that these black holes are in our very own Milky Way galaxy, and they may seem a bit elusive, so finding out more about them not only reduces the elusiveness of black holes, but helps us learn more about our own universe. Now, our second goal is to have fun always. Always have fun. Now, speaking of fun, the fundamentals of this lab include parallel and perpendicular components of force, and here we see the changes in momentum and how the F net relates to the derivative of momentum with respect to time. Now, we're also going to discuss the gravitational forces and the resulting effects of this kind of interaction. And how are we going to do that? Well, shout out to Newton always, and specifically this time for his law of universal gravitation, shown here, highlighting the fact that we want to find the mass of the black hole. And the MS just stands for mass of the star. Now, some initial conditions that we used to really get our code up and going, and here are some other calculations that we used to continue manipulating our code in order to achieve this just beautiful trajectory. Look at her go, or him, or whatever, Wow, that is just, we really wanted to find the mass of the black hole, and that was our quantitative objective. And here we have it, 7.36 times 10 to the 33 kilograms. If we want to go into more of the qualitative, the concepts of this lab. So, what does it mean? How do the net force and its parallel and perpendicular components differ from the rate of change in momentum and its parallel and perpendicular components? Okay, so going to net force first. When the object is speeding up or slowing down, these changes really have to do with the parallel component, and if an object is curving or changing direction, that has to do with the perpendicular component. Now, going to change in momentum. The parallel component really has to do with alterations in the acceleration or the rate in which the object's speed is changing, and the perpendicular component, on the other hand, has to do with how the nature of the path of the curvature or the rate in which that path changes and how those are affected. Now, imagine, we love a good what if. Imagine the black hole whose mass you found was removed and a different black hole was placed in the same location with the star's motion unchanged and the motion affected only by the gravitational force of the new black hole. Can you tell the difference? Well, let's talk about it. Let's break it down. Since Newton's universal law of gravitation uses the mass of the two objects, the magnitude of the distance between those two objects, and the gravitational constant, in order to obtain the magnitude of the gravitational force between the two objects, solving for the new black hole's mass when you keep the star's path, mass, and distance from the black hole the same would result in the same answer. Thank you, Newton. And thank you guys for coming to my TED Talk. Have a good one.